Welcome in this video where I'm going to introduce you to spherical harmonics. So in a lot of fields, for example in quantum physics, in graphics, we want to model functions on the sphere. So for example in 3D Gaussian splatting, we want to model the view-dependent color. So we want to model the fact that the color is a function of the viewing direction that can be modeled by theta on phi. On basically spherical harmonics, you can really see that as Fourier functions. So you can see that with a nested sum of y. I'm going to introduce y in a bit, but you can see y is a set of patterns. So we have a lot of patterns. We start from recurse patterns, and we can, if we add more terms in the sum, we can go from coarse patterns to finer and finer patterns. And basically by combining them, by weighting them with this coefficient CLM, I'm going to define that in a clearer way in the next slide. But basically, you can see you can think of a lot of patterns, recurse patterns and refined patterns, and basically you combine them, you weight them, and by doing that, you can model very complex functions on the sphere. Okay, so in NeRF and in Gaussian splatting, this is usually used for modeling the view-dependent color, but it's used in a lot of other fields such as quantum physics. Okay, so for example, here we can have a look at the mathematical formulation. So as I said, here we have a nested sum. The first sum models the frequency, basically the frequency of the patterns, the details we are going to use. The higher L, the better. The more complex functions I can represent. The smaller errors in my approximation. But that also means more memory on more compute. The CLM, these are weighted terms. We're going to come back to them in a moment. But basically, the more L I use, the more coefficients CLM I need to store, and therefore the more memory I'm using. Okay, on basically YLM. So YLM, this is mathematically defined. So it's just like this. It's mathematics. It's defined. So basically, if you know LM, theta, and phi, you can compute Y. On basically CLM, if we come back to that, CLM, these are the coefficients that the weight that are weighting each basis function. On basically CLM, these are the coefficients we need to learn. We learn them to model a specific function. Okay. On basically in Gaussian splatting, so this is CLM that we learn. For each Gaussian, we need to learn those coefficients. So you can see that here with this inner sum. So when L is equal to 0, we have only one term in that sum. When L is equal to 1, we have a sum that goes from -1 to 1, so we have 3 terms. When L is equal to 2, we have 5 terms. And when L is equal to 3, we have 7 terms. And with Gaussian splatting, we usually use 3 terms. Well, we use 3 degrees. We use spherical harmonics with degree 3. So that means that big L is equal to 3. And that means that in total, we have 16 spherical harmonic components, okay? We go from 0 to 3, so we have 1 term, plus 3, plus 5, plus 7. So that gives us in total 16 parameters, and we need to do that for each color channel separately, okay? So we need to do that for the air channel, the green channel, and the blue channel. So that gives us 16 times 3, so 48 spherical harmonics components that we need to store. And basically that's more than 80% of the total Gaussian parameters. Because with the vanilla 3D Gaussian splatting paper, with 59 parameters per Gaussian, on 48 of them, so more than 80% are just to model this the color that is view dependent. Okay, so that's very important to know if you are working with Gaussian splatting or if you have upcoming interviews. This is going in depth on these are things you need to know. So basically, as we said here, that's just a simple sum. CLM is just a coefficient that we learn. So let's have a look at YLM. Let's have a look at YLM. Because in some code you will see some coefficients, but if you are unsure where it's coming from, now you will understand. So basically, with this formula of YLM. Maybe I can give more details in the description on where it's coming from. But basically you can see first you have NLM. So NLM is really easy to compute. It's just the square root of some function. That is a function of L, M, the fractal function on pi. But basically if you have L, M, L on M, you can easily plug it into this formula and get NLM. Okay, so very easy to compute. Then with a polynomial, that's a well-known polynomial. And basically, if we have Lm on theta, there are tables, and we know the value of this polynomial. We can evaluate it. And then with a third term, that is a function of phi and m. So basically, based on the value of m, we either use the cosine or the sine. But basically, then with this formula, I have a formula. If I know Lm, theta, and phi, I can plug everything in the formula and get the value I need. This is using theta and phi, but usually instead of working with theta and phi, we work with Cartesian coordinates. So we work with x, y, z. So basically, I can do I can do a change of coordinate system and work with x, y, z, and therefore ylm just becomes a polynomial in x, y, z. Okay, and if I solve this equation, again here. Basically, you have all the tools you need to do it analytically on a sheet of paper. But basically, you can compute y of 0, 0. That's just a constant. So that's if you use spherical harmonics of degree 0. If you use spherical harmonics of degree 1, there are those 3 extra terms. So you can see that y1 minus 1, it's a function of just y. So it's a constant multiplying y. Then you have y10, y11, okay? If you want to go up to degree 2, then there are those 5 extra terms that are slightly more complex, but just simple patterns that are function of x, y, and z. And then if you go up to degree 3, you have those extra patterns. So now when you use spherical harmonics in your code, for example, there is this paper Planoxel or this paper Planoc 3 related to neural radiance field. I've implemented those papers in this YouTube channel. I will put the link in the description if you're interested. But basically, in all those code, or even in the 3D Gaussian Splatting code base, you see those coefficients that are encoded. So now you understand where they're coming from. Okay. So I hope this video was helpful to you. It's coming from my course on 3D Gaussian Splatting. If you want to understand all the details of Gaussian Splatting, all the details from the camera calibration to the training and to the rendering of the Gaussians, everything is explained in depth. And I will put the link in the description. Thank you.